Hi everyone, in this video we are going to begin talking about ionic compounds. But before we can dive really deep into it and talk about all the amazing physical properties that they have, I need to go back and review some definitions. So I want to start off by talking about ions, specifically cations and anions. So let's start with the very global term, so ions. So ions are essentially an atom, but technically it could be a group of atoms, or group of atoms with a charge. So it's a very simple definition. So examples of ions are usually sodium plus, or you could have chlorine minus, or a very common one is the phosphate ion, and so that's PO4, and then overall as a molecule it has a -3 charge. And so we would refer to this as an ion because they all have a charge, all right? So if it's a neutral compound, something like if we just wrote chlorine and it has a 0, this would not be an ion because it's not positive or negative. All right, so now these types of charges here, these ions, whether or not it's positive or negative, actually have a specific word associated with it. So the first one we always talk about is a cation. And a cation is simply an ion with a positive charge. So out of the examples that I provided above, the only cation we have is a sodium plus. And then an anion is simply an ion with a negative charge. Okay? And so the big example we have above would be our chlorine minus. And technically PO4 3- is also an anion, but we have a different word for that. We usually call them polyatomic ions. And so I'm going to actually talk about that in a completely separate video. So we'll come back to that later. All right, so now this is ions. We have cation and anion, And so now what I want to do is talk about what happens when we bring a cation and an anion together, which we all know, hopefully by now, that that would be considered an ionic bond. And so by definition, an ionic bond is essentially the bond between a cation and an anion. Cation and an anion. So it's pretty straightforward. And so an ionic bond is always the result of an electrostatic attraction, because we know our cation is a full positive charge and our anion is a full negative charge, or it could be -2, 3, 4, but at least it's a full charge. It's not a partial charge like we talked about before with covalent compounds. So these are full positives and full negatives. And so when we write out ionic bonds, we always write sodium plus and chlorine minus like this. You would never write out an ionic bond like that, because this implies a sharing of electrons, and there is no sharing of electrons in an ionic bond. So I'm going to put a big X to this and write no right next to it. Do not draw out an ionic bond like that. It's full positive, full negative. It's an electrostatic attraction. Okay, that's the big part of it. Now, in truth, okay, in honesty, out in nature, when we look at an ionic compound, it's actually not just one sodium and one chlorine. It's actually something that forms a big cage, actually, which is kind of called a lattice, or usually called a lattice. So in definition, we would say we have an ionic compound, but an ionic compound is a group of ionic bonds. Okay, so that's usually the part people forget. It's a group of ionic bonds that form a three-dimensional structure, or a 3D structure. But the important part is this next segment. While maintaining the same cation-anion ratio. That's the most important thing. So for an ionic compound of sodium chloride, we always are going to have 1 sodium to every 1 chlorine. You're never going to have 2 or 3 sodiums for every 1 chlorine. That's just not how it would work. So the lattice of sodium chloride actually looks like this really neat little cage. And so you draw this out in like kind of a box structure here. And we're using the long lines that appear to have a covalent structure, but really that's just a way to kind of signify the box structure. We're just trying to show you three-dimensional spaces, okay? So basically what we have here is what's called a lattice. and it's a lattice of sodium chloride. But realistically, this right here is actually our ionic compound. So it's a group of ionic bonds. It forms a three-dimensional structure, but it always, always, always has one sodium to every one chlorine. And so if you look, every corner alternates. We go sodium, chlorine forever, okay? So now there's two properties we need to understand when we talk about lattices, okay? We need to be able to talk about their strength, but the strength breaks down into two different sections, either the charge or the size of the atom. So let's start off by looking at the charge. So the higher the charge, the stronger the lattice. The higher the charge, the stronger the lattice. So now when I say the stronger the lattice, I'm saying that how difficult it would be to break that lattice apart, to separate that huge group of ions from each other, okay? Or in another way of saying that, how difficult it would be to remove one formula unit out of that lattice structure. So to remove one sodium and one chlorine. So the higher the charge, the more difficult it is to break it apart. So in my example here, I have a +1 and a -1, so a sodium and a chlorine. So that's a fairly low charge as far as ions are concerned, right? So it's a 1 and a 1 right here attracted to each other. So you could kind of think of it as hooking like this. Now, let's say I talk about something like magnesium oxide, something that has a +2 and a -2 charge. So if these two come together, it is a much, much bigger electrostatic interaction. It's a very positive atom attracted to a very, very negative atom, or ion, I should say. And so that charge, that attraction between the two pieces is so deep, and they're so much in love, basically, that it's incredibly difficult to break it apart. So the main point of this is, the higher the charge on your ions, the stronger the lattice. Now the second part of that is if we talk about the size of the atom. And so basically the smaller the atom, or ion, okay, because we're talking about charges, the stronger the lattice. So now for this, it's easier to think about having some kind of tube or vase or whatever you want to think of it, and think about how easy it would be to fill your vase with sand, right? They're very, very small particles. They easily pack well together. There's not much empty space. You can't physically see any air or anything. You can't see through the vase if you fill it all up with sand, because it packs so tightly close together because they're small. Now consider dumping all that sand out and filling it with something like golf balls or racket balls or lacrosse balls, something that are much bigger. If you stack bigger things on top of each other, they cannot get as closely. They cannot pack as tightly. And so if you were to do that inside of a vase, you would clearly be able to see through it in certain parts, because there's gaps of air or gaps of space where it's not packing tightly together. So in theory, the smaller the atom or your ion, the stronger the lattice, because you're going to be able to pack more charge together. So you can fit more sodiums and more chlorines together. They can all come together. Now that's a lot of positives and a lot of negatives all bringing closely together, and that is a strong lattice. So the higher the charge, the stronger the lattice, or the smaller the atom, the stronger the lattice. Those are our two big pieces. All right, now I'm going to end this section right here by talking about one more thing that we've discussed before, because remember, this is a quick review video, and that's an electrolyte. So we discussed electrolytes in the context of our nutrition unit, or the food we eat, and so we just want to remind you here that electrolytes have everything to do with ions. They are ions. Remember we talked about those 5 crucial ones. So an electrolyte, just to remind you, is an ionic compound, and usually that ionic compound is our solid, and so usually our ionic compound is your solute, okay, just to kind of give you more context for these words. So it's a solute that conducts electricity in an aqueous solution. Okay, so now you know what all these terms mean. And so hopefully when you think about electrolytes and you go back to thinking about your minerals, everything starts to make a little bit more sense, hopefully. So a big example of that would be sodium chloride. If I put sodium chloride or salt into water, it's clearly going to conduct electricity, and we definitely have an electrolyte. All right, so to end this video, I want to have a couple questions here just to see if you understand everything we said. So I'm going to give you a couple examples. So we have F-, S2-, we have Mg2+, we have Fr+, we have what is called salt, so I'm asking about table salt, and then sugar, so whatever you use for sugar when you're baking. I want you to classify these as either a cation, an anion, an ionic compound, or a covalent compound. Okay? So I either want you to say that it is a cation, an anion, an ionic, or a covalent compound. go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. Don't get frustrated. The first thing you want to do is identify your anion, so anything that has an overall negative charge. So right away I see that my F minus is definitely an anion, and I have an S2 minus, definitely an anion, because I see the negative charge right there. That's what indicates the anion. So now to identify our cations, all I'm going to do is look for my positive charges. So I see one right here and one right here. So my magnesium and my francium are both cations. Now I have to go and investigate what salt is and what sugar is. So we know, because I just told you, that table salt is sodium chloride, and sodium chloride is definitely an ionic compound. Okay? Ionic compound. Now sugar, we know from a previous unit of the food that we eat, that sugar is actually sucrose, and when we looked at sucrose, we knew that it was definitely a covalent compound. So hopefully that was pretty easy for you. If it wasn't, you need to take a second and go back and review all these terminology and make sure you can classify everything as an anion, cation, ionic, or covalent compound. All right, the last thing I'm going to ask you is I'm going to give you three different things. You have salt, same as sodium chloride right there, that just as I said before, sugar, and then water. Of these three, which one is an electrolyte? Go. All right, did you get an answer? Hopefully you did. In order to identify an electrolyte, you're looking for an ionic compound. So it is something that is a solid component that has a cation and an anion that you are able to dissolve into water. So there's no way your electrolyte can actually be water. That's your solvent. That's what you put your solute into, your actual electrolyte. So now sugar, we just said, was covalent, so there's no way that could be it. Salt is an ionic compound, definitely a fantastic, wonderful, beautiful electrolyte. Take care of yourself, drink lots of water.